So explain what the different ways to represent compounds. Why are there so many, right? So this is the concept of structural formulas. Structural or molecular compounds, or actually, I mean, it's in terms of there's actually two different ways to look at it. There's a ways of looking at in terms of diagram and versus formula, right? So when we talk about diagram, it's more so for organic chemistry, right? For in diagrams, there are like three different ones, right? We have structural diagrams. We have a condensed structural, which is the same thing as structure, and we have line diagrams, right? So for example, a structural diagram of ethene would look something like this, right? Ethylene would look, we have a CH2, double bonded CH2, right? And for a line diagram, we would just get simply just that, right? So these are two ways to look at diagrams here, and we can also look at them as formulas, right? So as formulas, I'm going to do them in red, and we can look at, there's two different types of formulas, right? There's empirical formulas and there's molecular formulas, right? I misspelled molecular formulas, right? So for example, if I'm taking, this is ethylene as an example here, the empirical formula for ethylene would be, I'll just in red, would be just simply just adding, I'm adding all these compounds, right? All compounds. I have 2 carbons and 4 hydrogens here. So it'd be simply just C2H4, right? Would be my formula here. And in this case, the molecular formula is the same thing as my empirical. It's still C2H4, right? So, but if you recall, actually, so it's C2H4 would be my empirical and my molecular formula in this case here. And remember, what we can do with molecular formulas is if we have different compound here, it's simply just a ratio, right, for molecular formula. So if we had something like, we can multiply this here by 2, you get C4H8, right, which is a totally different compound. It's not ethylene anymore, but this would be the molecular formula, and this here would then be the empirical formula, right? So again, empirical formula, you could think of it as the lowest terms, but when we think about lowest terms, it doesn't change it always changes the integrity of the chemical formula, right? So there's a limit as to how you can express both of these things in terms of formula and in terms of diagrams. So again, a diagram is much more specific. It shows you bonding. It shows you how atoms are connected together. So diagram is actually much better than a formula here. C2H4 and C4H8. Again, there's isomers with this, right? Not with ethylene, but with this one here, with butylene or butene. There's structural isomers here, right? So again, here it doesn't account for those ones here. This could be connected in a cyclobutane form, and I wouldn't be able to figure that out with the molecular formula. So in this case, we have to use both of them for us to infer both the geometry, the atoms that are present, bonding, and all those things are needed for us to, so we need to have both the formula and the diagram for us to represent different compounds. So hopefully that answers question 5 here, when we use diagrams and formulas to represent geometry, type of bonding, even atomic size, really. Size can be kind of represented, electronegativity can be represented as well, and obviously number of atoms in the formula here. So diagram has its perks, but the formula also has its perks as well. So that's great. So that's question 5 here. Let me look at the problem here. It says the chemical formulas and molecular models. So it's kind of the same thing. They broke it down to empirical and molecular formulas, which is great. Structural formulas and molecular formulas, space filling. They talk about bonding. You talk about molecular shape and orbitals as well. And they talked about how relative number of atoms and molecular formulas, actual number of atoms, which is great. So yeah, this is a good explanation. It's basically a summary of what I kind of said. So great summary, great solution and analysis here.